Hello everyone, I'm Nikos Raptis. I'm a senior engineering manager at Beat, and today we're going to talk about microservices design patterns, or if you like, some good practices in the microservices world. And of course there are a lot of ideas and patterns and solutions out there. We cannot cover everything, but I will try to give you some good examples of good practices and patterns that could be a good start if you are, starting to transition to this architecture. Of course, you should always evaluate what are the benefits or pitfalls of everything you try to implement in this architecture, because it's completely different world from a monolith, and you have different and a lot of new challenges to worry about. So make sure you do a good research when you're trying to apply a practice or a pattern. But yeah, let's move forward and try to see some of them. So the first, let's say, practice or pattern I would like to discuss with you is the Strangler pattern. Is useful when you try to transition to microservices, and its basic idea is to try to identify a boundary in your legacy application, as you can see in step 1, and make it a candidate for a new microservice. But before that, what you should do is create a Strangler facade, which actually is will be a mapper between the API of the old API of the legacy system and the new API that you will create for the service. So in step 2, actually what you do is you are creating this endpoint here for the Strangler facade. It could be part of the legacy system, could be something like a service, like a facade, but being a service inside the legacy system. So the important thing is that it expects the same format of the client that uses this kind of the code in the boundary. But then what it does, the facade, is to translate this request to a new request that is created as part of the new microservice, which might be different from this one, right? So you need kind of a mapper, because when you're designing the API for the initial system, the request might be different from the case that you had it in a new service, or a service that does only this specific thing. So you need a kind of facade, or a mapper that does this translation. But in the step 2, this doesn't do anything. You make sure that you receive the data, you store the data, or whatever you want to do with the data, but you don't have any response to the client, right? So actually the control passes back to the boundary, to the legacy system, and it continues to do what it did before. But in the next step, you have some functionality here ready to be used, so you can starting using the Strangler facade as an actual as the actual implementation of this service. So the client now has to normally you should not change anything for the client, because the facade is expecting the same kind of request, the same data, and translates the data, and then it passes to the service, which the service does what it does, and give the response, and the Strangler facade gives that to the client. I'm missing an error here, but yeah, you can imagine that it handles the response. And of course, you do not want to delete the boundary, the code from the legacy system yet, because if something goes wrong, you can switch to the legacy system, and you can have you don't have any downtime. But until you are sure, it's good to have this backup, so you don't delete that, and you should implement a mechanism. So whenever it goes something wrong here, you should fall back to the legacy system. But when you are ready and you are confident that this is working as expected, then you can delete from the legacy system the part of the code, and you have the client talking to the new service. Maybe you could proceed a refactor to the API, and then have it directly talking to the service itself. A variation of the Strangler pattern might happen in step 2. So you don't have to wait for the full code to be moved to the new service. You might have parts of code that produce something, and then you can have in step 2 a response to the Strangler, a response to the legacy, and you have an aggregation from the data that this part prepared for the client, but also what response the new service prepared, and you can aggregate them here and return them to client, right? This is a variation of the service. So on the right side, you can see something we did for a similar case in our monolith. We had a service, not a service, like a functionality around the device. So we said, okay, this is a device service that we, does some things for the device, like identifying the device, associate the device with an entity, and so this is kind of a boundary for us, a functionality that we wanted to separate. And initially this was a concrete implementation in the monolith. This is the interface, but it has a class behind it. It's written in PHP because the monolith is in PHP. The microservices are in Go. But yeah, this was it had an actual implementation of the device service, but when we extracted it to a new service, at some point we switched, and instead of the dependency injection, which is a custom implementation in our case, didn't return the actual implementation of the service, but what it returned was an HTTP client. And with this client, the actual client of the functionality here could use to make the request to the new service. But for him, it was like calling calling the same interface. So nothing changed for him. We didn't have to change the API, but yeah, this is an example of how you can do it in your monolith, and how you can, instead of returning an implementation, you can do a custom dependency injection mechanism to have it as a HTTP client. Now let's talk about boundaries, right? We said in the previous slide we identified some boundaries and we extracted them to a new microservice. But how we identify boundaries, right? What is the best way to do that? And I suggest, whenever you have a case that you need to create a new service, or identify a boundary in the monolith, it's good to use domain-driven design, DDD, right? Because the tools and the way of thinking and the practice and the options you have when you're using DDD are the best for business, because you're creating systems that are close to business. They're dealing with real business problems, and also use the same language as business. And what DDD says about this kind of boundaries is it is proposing something called a bounded context. And the bounded context is an area in your system that deals with a very specific business case, or some business requirements very closely related. So in the book of Eric Evans, Domain-Driven Design, it's a big one, but it has very good examples of how you can define bounded context, what is a bounded context. And as you can see here, it might, in the world of microservices, the good thing is that since microservices bring a good separation between them, and you don't have pollution like dependencies between the components. And when I mean dependencies, by communicating between them, but dependencies like libraries and all the bad stuff you have when you have a monolith with your code is it's like a macaroni after some years. So the good thing is that they have a very good limit of functionality, and they have hard interfaces. So you cannot share libraries between two services. not share code, you have to duplicate the code, right? So this is a strong boundary, and because bounded context is it has also strong boundaries. You can have, for example, a microservice as a bounded context, which does a very specific thing for the business. But in some cases, you might need more than one microservice to work as a bounded context, because having one microservice might be very turns out to be very big, or you might have different parts of the service that need different scalability capabilities and resource needs. So, for example, you could have a service that needs a lot of instances and a lot of CPU and RAM, but you have other services in the same bounded context that have a low need of resources, and that way you can might need to split them for that case. But ideally, you want every service to do something for business requirements. And again, I have an example here. In our case, we have a bounded context named driver account management, and this is what it says. It's a bounded context that everything here has to do with the account of the driver, from the registration to other functionalities around the account. For example, if we want to block a driver from making rides, etc., his personal data and personal information, and also some other interfaces for some mobile and back office tools. So, for example, we have the driver account microservice, which handles the data of the driver and the state of the driver, and we have another microservice which has the documents that the driver uploads during registration, which affect the driver account, right? You cannot have an account if you have not uploaded the documents, and the documents, they should be reviewed by a web application in the back office from an agent, and for that reason we have a web app backend for frontend service that communicates and handles the documents in the driver account. But also we have a driver mobile backend for frontend, which is the backend of the mobile client that they're using it to upload documents to the driver documents microservice. And we have another one which focuses on driver onboarding with material, videos, and FAQs, and content which could be translatable for the driver to understand the registration process, and also to answer some very frequent questions. So this is an example in our case of a bounded context. And on the right side you can see we have another one which is called referrals. It's a single service, but it's also a bounded context because it handles the referrals from the driver to driver, and it handles also the campaigns that we do for giving some bonuses to drivers that refer other drivers, and these drivers are making rides with us. And we had a conference page that we described what is the business requirement for the service, what the problem, what is addressing for the business, what's the functionality, and also we created a ubiquitous language for the business and for the engineering team, so everybody knows and uses in the database model and the model of the service. For example, what referral means, what referrer means, or what a campaign needs, what the enrollment criteria are. So this is also a very good step, a very basic step when you are implementing, when you're using domain-driven design ideas to create and design your system. So let's go to communication, and of course, maybe you have heard already that the best way of communication between services is using asynchronous messaging, because in that way you have services that are loosely coupled, and it's a good thing because having them communicating asynchronously, you don't need to depend on you have the dependency on the service is not very hard, because for example a producer, one service can create a message to a stream or a queue, and then it doesn't care, right? And you have other consumers or new consumers that join the system, and probably they could be interested in that event because it's produced from a service that they care about, and they want to know about what changes are happening in this microservice from business perspective, I mean, and they could do something. So they can just hear the message and the event from a stream or queue, and then do their own work. And this is a very good way because the producer does not have to know the clients, I mean the consumers, and it just have to propagate what changes in the area that it addresses, in the business area that it addresses. For example, if we get the previous example with the driver account, the driver account can produce a message whenever a field of his account information changes. If I change the name of the driver, then I could produce an event to a topic, and then the consumers that care about changes in the driver account information, they can for example, if you have a payment service that reads the information from the driver and creates some invoices for the driver, could use this new information to update its invoices payload, right? So in general, you want to do that. You want to have asynchronous messaging, and what we did in Beat, we used also a protobuf, and there are some reasons behind it, and we liked it because first of all, you can have a documentation for the payload automatically generated, easily generated when you use a protobuf, and apart from that, we could the other reason is that we were able to apply schemas, and we have the schema registry, as you can see on the top right corner, and you can have you have different versions that could break the integration with other services, but if you put it under a schema registry management system, then every service could monitor these changes, and then it could apply and switch to the new version of the payload. It's more controlled than having just a JSON payload where you cannot apply a schema. You can of course do custom solutions, but yeah, there are out there are better solutions when you're working, for example, with protobuf, and you can have a ready for use schema registry, and you can have the clients sign to the schema, and they are informed if the payload of a message in a Kafka topic, for example, changed, so they know it. So, and you can find this kind of changes before production. You can have tests around this, so you can catch it in the staging environment. So I think I don't have anything more for this kind of pattern. This pattern, which is actually try to use asynchronous messaging in the microservices world because the benefits we discussed, and if possible, try to create a schema because you want to be informed. A service should be informed when something in the payload was changed, because when you do a synchronous call, it's more easy to capture failures like this, right? So it's a way to be more protected when you are in the asynchronous architecture. So continuing on communication, what I would like to point out here is a very important practice or pattern, let's say, is having idempotent consumers. And what that means is try to be shielded from duplications in on handling the same data. And this can happen. It could easily happen actually in the when you have a microservices architecture. And as you can see in the right image, for example, let's take a service that sends a message to a broker, and the broker acknowledges, and then sends a second message to the broker, and the broker acknowledge is is failing here, and it's failed to be delivered to the service. So the service at that point still thinks that he didn't manage to send the B message to the broker. So what it does is try to send it again. And from the consumer perspective, what you might have is something like that. You have the A message, you have the B, and then you have again the B message. And if you don't pay attention to the content or have a mechanism to identify similar data, or the same data has been transferred to you, then you might have duplications in your database, in your local database. And I can give you a very specific example of a case that we had in the service. And on the right side, we had in referrals, when a referral does some rides, we want to record these rides and increase the completed rides, storing also the ride ID. And for the campaign, the referral campaign, when the driver reached a specific amount of rides, we gave to the referrer some bonus, some amount that to thank him because he brought a new driver, and this new driver did a specific amount of rides with us. And but what we didn't foresee here before the green arrow, because this is the line that we added it later on, we blindly increasing the completed rides, but the fact was we had rides or messages in the topic that we were consuming, or events that was the same ride. And this happened because the client, the mobile client, had a bug, and he was sending twice that the ride was completed. And we didn't make any check that this is the same ride that we're talking about, and this is a duplicate in our case. So what happened is we lost some money by paying earlier to drivers this amount of completed rides, and in some cases some drivers didn't do the actual rides, the minimum rides that are required to do to take the money. But of course, of having this bug, we gave them money because we have duplicate rides, and we're blindly increasing the amount of rides. So when we found out this, we tried to make this the referral service idempotent. And what we did is adding this line here, which said if the referral has this ride already, we create a warning in the logs, but then we return. We don't count this ride, because as I said, this was a problem of duplicate messages in the queue, in the Kafka topic, sorry, and we had to make our service independent of duplications. So this is a very important pattern to have in mind. Next one is a circuit breaker. Maybe you are familiar with this pattern, but what it does actually is, in case that you have a failure to a second service, it tries to reduce the times that it will hit it, because it already knows that something is wrong. For example, you see in the diagram, you have a client in the first service, which you have the circuit breaker pattern, and how you send a request to the second service is we are talking about synchronous calls here, so not asynchronous. So you have a response, and then you have again a call, and then you have a timeout. So something is wrong here, right? And you try again, and you have again a timeout. So you can configure a limit to the circuit breaker, and if you're still receiving requests from a client that use it to forward to the other service because you know it has some problem. You actually you're responding to the client from service A. So because you already know that something is wrong here, you don't want to wait for another timeout because you know it may lead to starvation to your resources here or waiting time. So you return immediately to the client, but at some point you reset the timeout because you want to see what is happening to the other service. So then you let go, you forward again a request to the other service, and then again it depends. The state is half open, which means that if it is successful, then you go back to the closed state, which I didn't mention in the beginning, but you have some states here. Closed state means that everything is okay. Open state means that the circuit is open and you don't have actual connection to the service, actual request forwarded to the service. But here you have the half open, and what it means that at some point you forward again the request, and then it depends. If you have a healthy response, you go again to the closed state, so you are here again. But if you have again a timeout, then you remain in the open state for another amount of time, and you continue mocking the response to the client, the timeout responses. This is the basic functionality of the circuit breaker, but you can do something like this. We did in Beat. We're using the circuit breakers in some cases when we are talking about in external services. For example, we have a heavy dependency on Google, and we ask them, okay, give us a route estimation or a route path between two locations, right? But if this something happens here and we cannot connect to Google for a weird reason, then instead of returning to the client an error, the circuit breaker tries to get another provider. So what it does is switching the service and fall back to the OSRM free routing service. So you can use a circuit breaker instead of mocking the same request, the failed request from service. You can use it to redirect the traffic for a specific amount of time to another service, and then get the similar responses for the business needs. So it's a good case, it's a good usage of the circuit breaker apart from the default behavior. So let's talk about data management, and probably you already know that it's a good practice to have a database per service and not a shared database. The main reason is the whole idea of microservices. One important aspect is you have a high cohesion in your components, which means your services, and also you try to achieve loose coupling, right? Two major let's say architectural choices that produce better designs. So if you have a shared database, you don't have you don't have high cohesion because you shared your models in the schema, and also you're very coupled between two services. So I guess you already know this. So every service should have its own data storage, and in some cases probably one service would need a relational database and the other would need a NoSQL database. So it's also another layer of flexibility, and you can adjust whatever every service needs to operate. But this comes with a cost, right? All we know transactions, and we might have cases that we have a transactional flow that should spread or must spread between two or more services. And you can see here in the example, you have a passenger calling a taxi to a service which is called Find Taxi Service, and then you have a payment service that should pre-charge the credit card, and then when it's pre-charged, you should have the status of the request should be updated. And in a legacy system, you would have a single database and a monolith, and all these actions should fit in a transactions, but in a single transaction. But in that case, here you have to deal with multiple transactions, and here the SAGAS patterns are coming to the scene. And on the left side, you see the choreography-based SAGA, which actually what it does is, it's kind of it's not a single transaction, but every service handles its transaction separately. So you have number one, the request, then you store the request, you probably put a status like pending or something, and you immediately return to the passenger that the application is searching. But then you in step 4 you produce an event to a stream, and a payment service hears such event and tries to pre-charge the card, and then post this message to payments event, and in step 7 and step 8 this event is captured by the find taxi service, and it updates the request status to let's say some like pre-charge. But in any case, this does not mean that it will fail immediately if the payment service fails to pre-charge the card. On the contrary, the passenger saw a message in the step 3 like something like, well, yeah, we are searching for the request, and probably at some point later, if something goes wrong in this flow, the find taxi service would be updated status something like aborted, or maybe even a business decision could be, let's do the ride and let's charge this amount for the next time for this passenger, to have a credit or something like that. On the right side, you see the orchestration based SAGA, which is similar, but in that case the find taxi service is kind of an orchestrator, and actually it sends like an event which is mostly a command, not like something like you notify the world around you. It's like a command for other services, like the payment service which it says, okay, pre-charge, please pre-charge this credit card, and then the payment service says, okay, I did it, and you have a response from another queue, and step 6, the find taxi service read this response, and then it updates the status and then informs the passenger. It could be also asynchronous, synchronous call, this one, and not asynchronous, but the idea is that the orchestration based SAGA it's more closely to a transaction, like the old like the one in the monolith, but in that case you have a service that acts as an orchestrator and sends commands and wait specific responses in order to complete its work. So these are the most common patterns, let's say, for dealing with transactions in microservices. In any case, it's not an easy topic, and you should have mechanisms from failing recovery, and repeating the same process if necessary somehow, ideally automatically. But yeah, it's more complicated and complex, like dealing with a single transaction, which is in a single service. It's handled by also by the machine. The underlying database, either MySQL or Oracle. But the problems don't stop here. In the previous example, the find taxi service have to create a record in the database and then send a message to a stream or a queue for the other services to notify that you have a request, and the payments service, for example, should do something. But this is again, it has some pitfalls, right? What if when the find taxi writes the record, and then before it sends the event on the topic, what if it fails, right? And you have a record in the database, but an event never produced in the stream, so the other services will not know this change. So what you can do in that is to use the Outbox pattern, the Outbox messages pattern, and what it does is you include in a single transaction two things. First, you write in the table the taxi request, and then you use another table called, for example, Outbox table, a pending to be sent event, right? And you also, for you to know that, you know, I wrote something, I have a new record, a new request, but then I have a pending pending event to send to the stream or the queue. And you also need a separate function or service, which is kind of message relay service, and what it does only is reading the Outbox table, you know, in some in some seconds or minutes, I don't know. And what it does is, you know, find new records, and which means new events that should be sent, and in that way it's handling the request then to the stream. And you know, it's a kind of a better way of making sure that you know, that you have something to send, and you have a service that continuously monitor of what should be sent, and always try to send the event. It might fail, for example, for some time, but the record, the Outbox table, is waiting to be consumed, and it would be transformed to a message, and then update the status again to the same table. So it's kind of having two transactions, one for finding a taxi service, but then you make a promise that a message should be sent by putting it in the Outbox table, and then you have another service which has another transaction that it should read, publish, and then confirm that it is sent. So in that way you might have less risk of you know, having different state in the stream and different state in your local database. Last but not least, some reliability and observability best practices. Regarding reliability, you should have health endpoints, especially if you're working with Kubernetes, which uses this kind of endpoints to know that your service is up and running in order to make it available to the rest of the system. So it's a good practice to have these health endpoints. Actually, Kubernetes have two that you can create, the alive and readiness. You can find the details of what its endpoint should do, but in general it's very important to have it. And passing to observability, it's very important to have application metrics, because you are dealing with sometimes hundreds or maybe thousands of microservices. So you understand that, you know, you should know somehow what is going on to your system, and application metrics are very, very important thing to take care. We are using Prometheus and Grafana for this in B. And on top of that, you can set up alerts. Again, very important, because you cannot you know, monitor 24 hours per day what is going on with the graphs. So what you want to do is to set up alerts for maybe important parts of your services or important services, to monitor, let's say, some downtime. Here you can see an example of monitoring a Kafka topic and potential lag on the messages. And if that's the case, because it's an important service, we create an alert, we post it in a channel in Slack, but also you can set up pager alerts, and you know, if you have on call in your company, someone will wake up and you know, take care of the problem if it's very important. And you should have logs and distributed tracing. I mean, logs is you know, it's obvious, but if you have it all in one place, it's very useful to see what is happening in your application as one. And this is possible if you're using a trace ID to track a call between services. So distributed tracing is also a good practice and a good pattern to use. Finally, because most of the times when you're creating microservices, many things will be the same between them. For example, some security libraries or other libraries, or setup configuration and so will be the same. It's good to have a project or a template that you can reuse. For example, we have a GitHub repository that you can use some commands, and this will generate the basic skeleton of your a microservice. And yeah, this saved us a lot of time, and also it's good for consistency between teams, and the way that the teams are creating their microservices. That's all from my side. Thank you very much for attending to this presentation. And yeah, anything you need, you can send a question, and I hope I will answer you adequately. And yeah, feel free to send me anything.